Now we begin to consider the application of second-order linear and nonlinear equations, homogeneous, non-homogeneous, to various physical systems. Now we have mechanical systems, which we're going to start with, and we'd also have electrical systems. And we'll see how those work out. It turns out that the equations that govern the mechanical systems are identical, except for the symbols we use and the meanings of the various parameters to those that we use for electrical circuits. And there are very good analogies between mechanical systems and electrical systems. Mechanical systems, for most people, are a little easier to understand, so that's where we're going to start. Now, we're going to start first with three systems that have almost identical behaviors and practically identical equations. First is a low amplitude pendulum. You simply hang a mass from some support, pull it back, and let it swing, or hit it with a baseball bat. One way or another, get it in motion, and it will tend to swing back and forth. In the ideal case, there's no opposing force, and the oscillation will continue forever. The differential equation that governs this, and we've seen this equation before, is simply F net equals negative kx. The further we pull the pendulum back, the greater the force that tends to pull it back toward equilibrium. The net force is in the direction opposite our pullback, so we have F net equals negative kx, where we set up an x-axis where x equals 0 at the equilibrium position, the position where the pendulum hangs naturally with 0 restoring force, and position function x of t. So this x represents our position function x of t. For the pendulum, it turns out that the value of k is just mg over L, where m is the mass of the pendulum, g is the acceleration of gravity, and L is its length. Recalling that Newton's second law says that F net is equal to the mass times the acceleration being the second derivative of the position function, we translate this equation into the form mx double prime equals negative kx. Dividing through by the m, we get x double prime equals negative k over mx. And we can then express this by adding the negative k over mx to both sides and replacing the k over m by omega naught squared. Omega naught squared is simply, omega is our angular frequency. Omega naught is the square of the angular frequency of the pendulum, as we see when we do the solution. And omega naught has to be equal to the square root of k over m. In other words, in order to replace the coefficient of x from negative square root of k over, from square root of k over m to omega naught had better be equal to the square root of k over m, and replacing it by omega naught squared, not omega naught, as I said just a second ago. So we get this general solution, and we can easily verify that this is the general solution to this equation. And that general solution comes out very easily from the techniques that we've seen previously for second order linear equations. Okay, this solution also applies equally well to a mass on a spring where the mass is on some frictionless surface and the spring is an ideal spring. So this is an ideal approximation of what actually happens. So we have no friction, we have no energy loss in the spring. We have an equilibrium position for the spring. That's the position at which, if we release the system, the mass will experience a zero net force. Okay, no force pulling it this way or this way. So if we were to actually release the system and somehow damp the motion, it would come to rest at this point, x of t being the position, completely analogous to the way we've set up the pendulum. And in this case, again, we get F net equals negative kx. Again, assuming an ideal spring, that's simply the law that works for an ideal spring, and a well-made spring approximates this ideal very well. And from this we get the same equation that we had before, and everything else follows the same as it does here. Omega naught is going to be the square root of k over m. The only difference between this system and this is that here it's actually gravity, the way the gravity and the tension of the string articulate, that gives us the restoring force. Here it's the direct force exerted by the spring as a result of being stretched or compressed. In any case, we get a solution function that's of the identical form that we have up here. If we hang the weight so that we have some equilibrium position, the position at which the weight would rest without moving, and we set up a y-axis where y equals 0 at equilibrium and y of t is the position function. The position is a function of t, and we get an oscillation, an up and down oscillation. In this case, the F net would be negative ky, which is exactly the same as F net equals negative kx, except here we happen to be using y for the position function, and here we used x. So that our equation becomes my double prime equals negative ky, etc. Everything identical here except we're using y's where we previously used x's, and we again get a solution function of exactly the same type. In this case, the solution function would be a y of t, whereas in this case it's an x of t. But everything else is identical. In the ideal case, where we have no external forces, only the restoring force acting on the system, this is our complete solution. And depending on the initial conditions, we can evaluate the C1 and C2 to accommodate initial conditions of position and or velocity. And we should pretty well completely understand how that works at this point for the ideal system. Now, what if there's some friction here? There will be at least air friction, air resistance. There's probably going to be energy losses in the spring and some kind of drag force here. What's going on if we do have some sort of resistance? In that case, we have to introduce another term into this net force equation, and the net force is no longer going to be the ideal negative kx or negative ky. In that case, as we'll see, we're going to end up with a second order non-homogeneous equation, and we're going to have to use either variation of parameters or undetermined coefficients to solve the equation.